So as we saw, there is an age-metallicity relationship in the galaxy, as the overall metallicity of the galaxy increases in time as successive generations of stars enrich the interstellar medium. Clearly you see here this gradient in the metallicity. We have a terminology for that. It's an old terminology, but we are stuck with it. Population 1 are the young and metal-rich stars, and population 2 are the old and metal-poor stars. Now, where do we find these different populations? In different components of the galaxy. Galactic structure consists of a bulge, the halo, and the disk. It turns out young stars are found mostly in the disk, and population 2 stars are found mostly in the halo. And that is a remnant from galaxy formation. The halo is the first structure in the galaxy that forms during the collapse of the original cloud. You have the pre-galactic cloud falling in. As it conserves angular momentum, it starts to shape into a disk due to rotation, but meanwhile stars are already forming, and they form the halo. The disk forms later as the gas settles in. So then what you're going to have in the halo is disordered motion from the stars that were forming while the gas was collapsing. And in the disk, you have the ordered motion because you have the ordered rotation. So population 2 stars, they're old and metal poor, they're halo stars, where star formation has ceased long ago. Therefore, they tend to be red. Population 1 are young and metal rich, they're disk stars where star formation is still ongoing, so they tend to be blue. An example of population 1 stars are stars in young open clusters. Open clusters, they're usually young because they're formed in the disk. Now, because they're subject to the galactic tides, they're disrupted within a few orbits. They retain their physical integrity only for a few million years before the stars disperse. So mostly, they're still hanging around their birthplaces in the spiral arms of the galaxies. Indeed, most disk stars were born in open clusters, including the Sun. It's rare to see a massive cluster, a massive open cluster that is old, but they exist. There are old open clusters. For example, M67, which is 4 billion years old. It is an open cluster at this age because it's massive enough that it can remain gravitationally bound, withstanding the tides of the galaxy. In fact, it is possible that M67 is where the Sun came from. The metallicity is very similar and the age is very similar. Example of population 2 stars are globular clusters. Globular clusters are old system of stars in the halo. They are spherical, therefore globular, because they're massive, and gravity could shape the system into a spherical configuration. They are virialized, with the more massive stars going to the center and the less massive stars going in the periphery. And they are pretty much spherically symmetrically distributed around the galaxy in the halo. In fact, it was the survey of globular clusters by Harlow Shapley in the beginning of the century that gave us the first evidence that the Sun was not in the center of the galaxy. Right, so we talked about the halo and the disk. Now, how about the bulge? What kind of stars you find in the bulge? Well, in fact, the bulge stars are a little different. They are old and metal rich. This is a color magnitude diagram of stars in the bulge compared to this object, NGC 6528, which is a globular cluster. As you see, it has these older stars. So the turn off of the main sequence around here, all of the stars here are in the giant branch. This points to the bulge being an old structure, but it is quite dense. The star formation rate is proportional to the density. More gas, more stars. So the chemical enrichment was fast. Indeed, here you see the metallicity distribution of the bulge, and it is almost as metal rich as the disk. So a galaxy's density decreases with radius, so the star formation radius decreases with the radius too. The central part, the bulge, has a high gas density, therefore a fast chemical enrichment. The outer disk has a low gas density, so stars form more slowly. There is a slow chemical enrichment. So in the same way that there is an age-metallicity relationship in the galaxy, there is also a radial metallicity gradient. The stars closer to the center are more metal rich than stars in the outskirts, in the outer rim of the galaxy. This is why stellar population is a terminology that is kind of old. So population one is young and metal rich. Population two is old and metal poor. But there is this old metal rich stars in the bulge, and there are also young metal poor stars in the outer disk. So the use of stellar populations is sort of discouraged, and then you should use age and metallicity whenever you can. The exception to the rule are population 3 stars. Population 3 stars, they are different than population 1 and 2. So population 1 are metal rich and young. Population 2 are metal poor and old. Population 3 stars are metal free and extinct. They're supposed to be the first stars in the universe, when the universe was hydrogen and helium and nothing else. So this is a timeline from the Big Bang. Here you have the emission of the cosmic background radiation when the universe became transparent. And it was a dark age when there were no stars, and then the first stars were formed. We cannot see them because they are long gone. But the second generation of stars may still be around. Indeed, there are people that looked for this very metal poor object. You see here, there is this star. This is the spectrum of the star compared to the spectrum of the sun. The spectrum is almost featureless. This is an iron line. This should be a deep iron line as it is in the sun. And in this star, you see how little absorption there is. By the way, this is in the blue, where in the sun you have the significant depression. This star, in fact, has a metallicity of minus 5.2. This is about 300,000 times less iron than in the sun.